So my name is Natalie Wheeler, and the title of my talk is Spontaneous Raman Scattering in Hollow Core Photonic Crystal Fibres. And this work was carried out as part of a collaboration between the University of Southampton and IS Instruments, who are based in Kent. So spontaneous Raman scattering is an inelastic scattering technique whereby pump photons through scattering with molecules can be scattered to produce Stokes photons, which typically have a longer wavelength or a lower energy. The Stokes spectrum provides a distinct signature of the gas, which is what I should say we're talking about gas sensing here. So we're talking about Raman gas sensing. So it provides a distinct signature of the gas species. So if you have a gas sample which has got multiple species present, you will get several distinct peaks in the Stokes spectrum. And this makes it an attractive technique for optical gas sensing. You can have a single shot measurement with a short acquisition time and only use one single optical source to be able to get information on a wide range of species in a multi-component gas sample. Another advantage is it's relatively insensitive to water vapor. However, the Stokes signal is extremely weak when you're talking about scattering from a gas sample. It's a function of the parameters shown here, so the scattering cross-section of the molecules, the gas density, the pump laser power, the collection angles, the detected solid angle in the experiment, and also the interaction length. And what we're focusing on here is increasing the interaction length using what's known as hollow core photonic crystal fibres. So these are novel optical fibres in which light can be guided with low loss in an air core. And this means that we can actually put our gas sample inside the core of the fibre, where it's simultaneously confined with the pump light, and then it can propagate together with the sample over a long interaction length. And the fibre itself also acts to collect the Stokes signal. So there's been several previous works of looking at spontaneous Raman in hollow core photonic crystal fibres, and I'm just showing two examples here. This on the left is the first measurement from 2008 from Burek et al., where they had about 1.5 meter length of hollow core fibre, and they were just looking at detecting the components of ambient air. And you can see from this plot that they successfully were able to identify oxygen and nitrogen. Over the last few years, there have been several other reports with much better improved signal to noise and looking at multi-component mixtures. And there's one nice example here from Hamp et al., where they have many different components in their gas samples at different concentrations, and they can quantitatively analyze the composition of the gas, looking at all the different components in a single shot. And they have using a higher pressure of around 20 bar, they can get to a limit of detection with methane of 0.2 ppm. So we see from these and other results in the literature that this technique is promising. We can have a greater than 2 order of magnitude improvement over free space arrangements due to this long interaction length, simultaneous of detection of multiple gases with low cross sensitivity. You can also have a high dynamic range, so within one measurement you can look at very low and very high concentrations of gases simultaneously, and there are potential applications in industrial and environmental sensing and breath analysis. However, so far all these measurements have been in what we call bandgap guiding hollow core photonic crystal fibre, and it's mainly using commercial fibres. So in this work, what we're really looking at is what would be the optimal fibre for this kind of technique for gas sensing. And at the ORC, at the University of Southampton, we make our own hollow core fibres. And they're typically grouped into 2 different types. So on the left, we have the more well-established hollow core photonic bandgap fibres, in which all the previous measurements for spontaneous Raman scattering have been carried out. And on the right is a second family of fibres called hollow core anti-resonant fibres. And these 2 groups are distinguished by their guidance mechanism. So at the ORC, we make a lot of these fibres for applications in telecoms and laser delivery. But in this work, we're specifically thinking what will be the best fibre for the Raman gas sensing application. And as I mentioned before, up until this point, no one has really looked at the second family, the hollow core anti-resonant fibres, in particular for spontaneous Raman. So just quickly run through the key properties of both these types of fibre. So on the left, for the photonic bandgap fibres, for these fibres, we find that we have the lowest reported loss, which is around 1.2 dB per kilometre at 1550. They also have negligible bend loss, which means you can make very compact devices from them. However, from the guidance mechanism, they have a limited spectral bandwidth and also a limited range of core diameters. In the second family shown here on the right for the hollow core anti-resonant fibres, if you're operating at a wavelength below 1 micron, you can actually have a lower loss than in a bandgap fibre. However, there is a compromise where they have significantly high bend sensitivity. But we can have very wide spectral bandwidths. They can operate in different wavelength regions in multiple windows. And there's a really wide variety of structures that you can have, which enable a wide variety of core diameters and therefore mode field diameters. We also have a lower overlap of the guided light in the core with the silica cladding. So here we're thinking, can this second family of fibres, the hollow core anti-resonant fibres, provide any key advantages for the Raman-based gas sensing application? So we might think we've got a wider bandwidth, we can detect a wider range of Raman shifts from different gas species, so we can have a wider range of components in our gas sample. Also, if we've got lower attenuation at below 1 micron, which is typically where people are working for Raman gas sensing, we can use longer fibre lengths to make the signal stronger. We also have a lower overlap of the guided light in the core with the silica microstructure cladding. So one thing we can expect is a reduction in any kind of background noise, for example, from Raman in the silica structure itself. So here I show the experimental setup that we've used to compare the performance of these two fibres. In our work, we're using a pump laser at 786 nanometers with a maximum power of 270 milliwatts. If you compare this to other reports in the literature, this is a slightly longer wavelength than typical and a bit of a lower power, so the actual Raman signal strength is a bit reduced, but in terms of being able to compare the performance of the two fibres, we have plenty of signal, so it's not a problem. The laser diode is launched through a single mode fibre and a telescopic lens arrangement into our air-filled hollow core fibre under test. At the output, we remove the pump laser light with a filter, and then the Stokes signal is coupled into a multimode fibre and into our diffractive spectrometer. So the fibres under test is shown here. So we have one example of each type of fibre, bandgap fibre on the left and the anti-resonant fibre on the right. And these fibres have quite different mode field diameters, so the only change in the setup is that we optimise the lenses to get the maximum coupling efficiency in and out of the fibre for the two different tests. And I should mention as well, for this work, we're looking at the forward scattered Stokes signal. You can also look at the back scattered, and that's shown in other reports in the literature. So I'll just show you a bit more detail on the fibres that we're using. First, we'll look at the hollow core Photonic bandgap fibre. So here's a bigger image of the fibre, and on the left, we've got the fibre loss as a function of wavelength. We can see that we do have low loss in certain spectral regions, but from the bandgap mechanism, you only have a relatively narrow region of operation for this fibre. And it's also punctuated by what we call surface mode resonances. So these are wavelengths at which the low loss core guided modes can interact with surface modes which are localized in or around the core surround of the fibre. And these surface modes have much higher loss. So when those core modes interact with the surface modes, you get these peaks in the transmission or the loss spectrum. The second fibre is a Kagome structured anti-resonant fibre, and you see it's got a broader bandwidth, even though this is actually a higher operating window for this fibre, and it's got lower loss. The key wavelengths that we're interested in for this experiment is we're looking just at air-filled ambient air in the hollow core fibres. We've got our pump wavelength at 786 nanometers, and then two Stokes lines from oxygen and nitrogen, 896 and 963 nanometers respectively. And this table just shows a comparison of the loss of the two different types of fibre at those key wavelengths. So what we can see is that the anti-resonant fibre has lower loss at all these wavelengths. For oxygen, it's actually quite similar loss. For nitrogen, it's significantly lower loss. So here's the first results. On the left, we have the results for the hollow core anti-resonant fibre, and on the right for the bandgap fibre. We can see from both sets of data here that we clearly pick up the oxygen and the nitrogen Raman Stokes signals. However, we get much stronger signal actually from the bandgap fibre. So this is with exactly the same fibre length. In this case, a similar coupled power of around 50 milliwatts and ambient air inside both the fibres. we get a much higher number of counts in the bandgap fibre, and we do see a bit more background noise in this fibre, but even with that, we have a higher signal to noise ratio in the bandgap fibre. So continuing comparison between the fibres, we looked at the evolution of the Stokes signal as a function of power. So on the left, we're looking at the nitrogen signal versus power for both fibres, and on the right is oxygen. So just focusing on the left, we can see the black data and data points is for the bandgap fibre, and the blue data points are for the anti-resonant fibre. You can see there's significantly more signal that we're collecting from the bandgap fibre. This is particularly surprising for the nitrogen, where the loss is significantly higher. So this led us to think again about how we're comparing these two fibres, and one possible explanation is to think about the effective capture efficiency of the fibre. So this is linked to the, thank you, detection angle in that first equation that I showed you. So for our fibres, what we really need to think about is the numerical aperture. So how well they're going to capture the light. And in holocaust fibres, this is not actually a parameter that's widely discussed or necessarily fully understood, but values from the literature for an anti-resonant fibre, the NA is very low, around 0.02, so 0.02, and for a bandgap fibre is more like 0.12. So this can actually explain a very different collection efficiency and a much more effective collection efficiency in the bandgap fibre, even if the loss is higher. So is there any case where the anti-resonant fibre can perform better or have any advantages? One thing we can think is the loss is lower, so we can use a longer length. Here we're comparing 27 metres with 2.7 metres, so we've scaled up the length by 10 metres. This is just for the anti-resonant fibre. And we can look at the nitrogen signal and the oxygen signal. And as expected, we do see an increase in the amount of Stokes signal for using a longer length. For the nitrogen, we get about a factor of 6 increase, and for the oxygen, around 7.6. However, the observed increase is not linear because of the fibre attenuation. So we can just check that this is what we should expect from theory. So this graph shows the evolution of the Stokes power as a function of fibre length. And we can see the theoretical increase for oxygen should be around 7 and around 5.8 for nitrogen. So this is a very good agreement with what we see in the experiment. And we can see that even with a 10 times longer fibre, the Stokes power from the anti-resonant fibre is only just about becoming comparable to what we see in the bandgap fibre in a much shorter length. And just to say again, the different improvement for oxygen and nitrogen is down to the difference in the loss. So you have a higher loss for nitrogen, so you don't see such a gain if you make the fibre longer. So that led us to think, well, can we just make the loss even lower? And the answer is yes. The state of the art for hollow-core anti-resonant fibre is around 7 to 8 dB at 750 nanometers. So if we have a fibre where the pump loss is 5 dB per kilometre and the Stokes loss is around 5 dB per kilometre, we could actually then see an almost linear increase in the Stokes power. If we scale up the fibre, for example, from 1 to 100 metres, we'd see an improvement of around a factor of 90. But then you have to think, these lengths are very long. So unless you're thinking of distributed sensing, for a lot of applications, this is not practical. And you have to consider the implications on the response time of any device. So just to finally, we think about, well, the bandgap fibre seems to be the superior candidate here. Can we make it any better than it already is? So at the ORC, where I work, we focus a lot on 1550 fibres for telecoms. And the state of the art that we make have a minimum loss around 3.5 dB per kilometre for having a broad operating bandwidth, which you're going to need for this type of application. The loss in bandgap fibre scales inversely with wavelength to path 3. So we can say that if we shift our state-of-the-art fibre down to around 800 nanometers, we'd aim for a loss of 25 dB per kilometre. But in reality, we have to consider that that bandwidth of that fibre will be punctuated by surface nodes, and it will be limited. So you'd need some careful design of the fibre and positioning of those surface nodes to be able to operate it for whatever Stokes wavelengths you're interested in. Also, the fabrication of bandgap fibres for shorter wavelengths is more challenging, so achieving 25 dB per kilometre is not easy. Nevertheless, we'd suggest that tailoring the bandgap fibre for Raman and producing high-quality state-of-the-art fibres around this wavelength or even towards the visible would enhance the limit of detection towards the PPB level. So just to summarise, we got the first comparison of spontaneous Raman scattering in polycore anti-resonant fibres and bandgap fibres. In both fibres, we can see the nitrogen and the oxygen Stokes signals from ambient air, but what we see is that the signal from a bandgap fibre is significantly stronger in the same experimental conditions, potentially due to this higher capture efficiency. We could increase the Stokes signal by using a longer length of polycore anti-resonant fibre, but in a practical device, this may not really be the way you want to go. It depends what application you're looking at. And for many practical applications or fibre lengths, the bandgap performance would be superior. And further understanding of the capture efficiency in photonic crystal fibres could lead to potentially improved design. So thank you for our sponsors, and thank you for listening.